Good morning, a very warm welcome to all of you. Last class about magnetic materials, we have defined three vectors. Remember what it was that? B bar vector. Then another interesting vector which is H bar with a unit of ampere per meter. And then one more vector, the intensity of magnetization, capital I bar vector, or according to NCERT textbook, M bar vector. So the three vector and a relation between them. Along with these three, we have also defined two more parameters like relative permeability and susceptibility. We have given a very all important relation between them also. Remember, mu r is equal to chi plus 1. A result was given yesterday. Now, based on these values of mu r, the relative permeability and susceptibility, we have last class seen the classification of the magnetic materials into ferro, dia and paramagnetic materials. Now one more important property regarding magnetic materials we will now discuss. A very important topic because it will cover a whole lot of conceptual questions. Maybe more than 10-20 questions now you will find in our discussion. Our discussion is only for 5 to 7 minutes, but you will find, as I have told you, dozen or more than dozen number of conceptual questions and answers. Now let us see what is the property, popularly called as hysteresis property. Hysteresis and hysteresis loop, hysteresis loss. These three things are our point of discussion now. Now, yesterday we have told that H is the agency that causes capital I in the magnetic material. I refers to the net magnetic moment per unit volume. So, to convert any magnetic material into a magnet, we need the agency, and that agency is what is called as H, such that supposing in the beginning the net magnetic moment of the material is 0. So to begin with, no magnetism in the material, no net magnetism, so I equal to 0. Therefore, I is caused by H, we have told. H is a cause and I is a effect, yesterday we have told, right? Therefore, see here. Initially I equal to 0, now we start increasing the value of H, the agency. So as H increases, I also increases. Such that this IH curve, IH graph is also one important concept regarding our need and CT questions. How? Yesterday we have told about paramagnetic materials, ferromagnetic materials and diamagnetic materials. For all of these things, IH graph can be asked. Now that this particular graph we are showing it for ferromagnetic materials, I versus H graph in a complete cycle that now we'll discuss. Whereas the same question, I versus H graph, even before we get into this one, now let us see the point of I versus H graph for paramagnetic material, and so this is H versus I graph. First I am writing it for paramagnetic materials. Now here you have seen H can have negative axis and as well as positive axis. I also can have negative axis and positive axis, such that here I versus H graph is a kind of straight line graph we get for paramagnetic material with positive slope. A constant slope graph we will get for IH graph for, yes, paramagnetic materials. Whereas very interesting point is the graph of H versus I for diamagnetic materials. Now, we know that paramagnetism and ferromagnetism, they show the tendency of feeble attractions to strong attraction in magnetic field, whereas due to diamagnetism it will be a feeble repulsion property. What do we mean by attraction or what do we mean by repulsion? Always remember, in case of field concepts, the tendency to displace from lower intensity to higher intensity is what referred as attraction, whereas the tendency is to have the motion from higher intensities to lower intensities is what is referred as repulsion. Now, diamagnetism, they exhibit a feeble repulsion. What is meant by feeble repulsion? In the case of this can be, again I am telling you, you follow each of the statements for about 5 to 7 minutes or 10 minutes, you will find good number of questions and with answers. What is the meaning of this attraction or repulsion with respect to this dia, para, ferro? Then it means that when a diamagnet, when ferro or paramagnetic material is placed inside the magnetic material, that I that is developed, net magnetization will be parallel to H bar, I bar parallel to H bar in the case of para and ferro, whereas in the case of diamagnetic materials, I bar is always anti-parallel to H bar. That is the concept, and that is why when we are writing it for diamagnetic material, this graph is quite interesting. As I have told you, I, yes, in a direction opposite to H bar, therefore we will take the negative I values and we write like this. So this is what is the case for diamagnetic materials. Now whereas we are now discussing the same for the ferromagnetic materials, which is quite interesting, where again we come across more number of parameters and concepts, right? So do remember the graphs of I and H for para and diamagnetic materials. Similarly, yesterday I have told you about the Curie's law, dependence of susceptibility with temperature, susceptibility temperatures, the Curie's law, the graphs we have discussed in detail in the classroom. Go through those also. Now you see, as H increases, I increases such that it is bit nonlinear. It is not a graph with straight line you are getting. O to A I am telling. This A is what is refers to the saturation magnetism. Any magnetic material, by using H when we magnetize, when all the magnetic dipoles, atomic dipoles inside the material get that alignment, that is what is maximum intensity of magnetization, I, that is refers to saturation magnetism. Therefore here A refers to saturation magnetism. You just go on looking to the points. One more time I am telling you. Supposing if I take this one, this, yes. Now this intercept, supposing I call this intercept as some Y. Now here O, Y refers to saturation magnetization. Saturation magnetization, that is what is the I maximum. I maximum, and again in the direction of H bar. In the direction of H bar. Now, earlier we said I0, H starts increases from 0. This is what is the case that arises. Saturation magnetism. Now, let us start decreasing the value of H. Earlier 0 to this some value we have taken, right? This one. Now let us start decreasing H. It is quite interesting that as H decreases, you will now find here. You will now find here. Now as H starts decreasing, I also starts decreasing, because I is always an effect due to H, of course. As I decreases, H decreases, I also decreases, such that interestingly, when H is 0, I not equal to 0. H is 0, but I is not equal to 0. What does it mean? Now here I call this some point as B. I call this point as B. The material, now this actually explains us that, or the inference that we can draw is that the material which we are calling as aromatic material, do remember, this material is showing a tendency or showing a characteristic of retaining magnetization, regaining of magnetization even in the absence of H. Actually I is due to H, but even in the absence of H also, whatever I that has acquired, it will decrease but does not become 0. So it is showing the character of retaining ability of magnetization. So this point B, we call it as retentivity property. Retentivity property, the ability to retain the magnetization, retentivity, and this OB refers to, yes, that degree of retentivity. So more is this x-intercept, sorry, y-intercept. You see here, OB is a y-intercept. So more is the y-intercept, more is the retentivity, right? So this intercept because at the end of our discussion we will see the size of this complete loop is what is very important thing, which will give solution for a number of questions. So OB, this y-intercept is what is the degree of retentivity. Now that, say H actually started increasing from 0 to some maximum value, and then H we have decreased, and we have seen I not equal to 0 even for H equal to 0. Now therefore, for I to further decrease, if I want to decrease the value of I further, then what is to be done? The same H is used but in the reverse direction. So to decrease the net magnetization, we are reversing the direction of H, and that is why now we can see the other side of the axis. So this is what is H, the reversed direction H, taking the negative values for the vector we are writing. Therefore to decrease I, we are reversing the direction, and I gradually, again H is reversing direction after 0, H is reversing direction and gradually increased. I start decreasing such that here I write one point, I call this point C. At this point C, for this particular value of H, the intensity of magnetization becomes 0. So this C point now refers to coercivity. What is meant by coercivity? Earlier we said retentivity, the ability to retain the magnetization even in the absence of magnetizing field. Coercivity is the ability to oppose demagnetization. H reversed in direction means we are demagnetizing the material for which I is gradually decreasing and becoming 0. So this tendency or the ability or the character of the material to oppose demagnetization is what is referred as coercivity. Now, the degree of coercivity is what is OC, that is x-intercept. Remember, this OB is y-intercept. Retentivity is always y-intercept. It is y-intercept. Coercivity is I am writing as OC. It is what is x-intercept. That we will see that this OC is in the negative axis that we have shown. And one more thing, when we said OB, the y-intercept, then it refers to the value of I. When we said x-intercept, this OC, the coercivity refers to the value of H. Remember, coercivity refers to, it can be a question, retentivity refers to this, all these kinds of questions. And that is the meticulous observation, point by point in the graph. And that is what we are following. So first we go to A discussion, then A to B discussion, now up to B to C it is over. Now again, supposing beyond C also, if I increase the value of H, beyond C if I start increasing H, then I also starts increasing in the direction of H bar. In the direction of H bar. So remember, from B to C, H bar and I bar are anti-parallel, and from C to D if I write, from C to D again I bar is parallel to H bar. Remember, O to A, both I bar and H bar are parallel. A to B, of course, H was 0 or H was decreasing. Therefore, I was also decreasing, again parallel. H bar and I bar are again parallel for me. Whereas, from B to C, yes, I bar and H bar are anti-parallel. C to D, again H bar and I bar are parallel. Again, this refers to saturation mechanism. And again, we will continue the same which we did earlier. Again, the value of H decreases, the I value decreases, but no question of I being 0 for H equal to 0, the ability, the property of retentivity. Therefore, this E, if I call, OB and OE both refer to retentivity. And again, if again H starts increasing in the other direction, the same will happen. Of course, I call this point as some F. So now where the vectors I bar and H bar are parallel, where they are anti-parallel, where the value of H is 0, where the value of I is 0, what are the different terminology that we are using is what is the most important thing of our discussion. And again from F to A, again gradually. So this completes a cycle of magnetization and demagnetization cycle. In fact, I should say. So this entire graph represents the cycle of magnetization and demagnetization of a ferromagnetic material. The important points are, of course, saturation, magnetism, retentivity, coercivity, intercepts. Please do remember retentivity, y-intercept, coercivity, x-intercept, and so on, all these things. Now, another important point that arises when we observe this graph is, in this graph, we'll find that H lags I. So this is what we'll find. The lagging of magnetizing field with intensity of magnetization. This lagging of H with I is referred to our property of hysteresis. So hysteresis is a phenomenon of lagging. We are telling about the H with respect to I. Now the point is that, what is the consequence of this hysteresis? Here what we find is that the material is opposing demagnetization. The material is opposing H bar as well. Some places it is encouraging H bar and some places it is, discouraging H bar. And because of that, what happens? In the cycle of magnetization, demagnetization, there is loss of energy. Why the loss of energy? Yes, it is because of the property of coercivity. So because of the property of coercivity, there is loss of energy, and that energy, what is refers to? Hysteresis loss. This loss is due to the property of hysteresis loss. And most important point is that, another important point will add that all the things that we have discussed so far, each and every statement is important. Another important statement that we are adding is the area of this hysteresis loop is a measure of the loss of energy per unit volume. More is the area of the loop, more will be the loss of hysteresis due to hysteresis, and lesser the area, lesser energy loss is an important point to be remembered. When we said that, again look into the graph and just go on about your discussion, that for the area to be more, what are the conditions? For the area to be more, this intercept OB or OE, what we are calling retentivity. So more retentivity is there. Again the graph, and what happens? The area under the graph, what happens? And similarly this OC, the coercivity, supposing if it is smaller value or if it is higher value, how does it affect the area and hence the measure of hysteresis loss? Yes, of course I can give it in one or two statements, but do remember, you make the discussion. How this area under this loop will get affected is an important thing, right? So now the two more important definitions are retentivity and coercivity, and these things definitely matter in the choice of the materials. Choice of materials for particular cases. Supposing I want to make permanent magnets. To make permanent magnets, of course the material should be ferromagnetic, but which material will be a better one? See, when we say permanent magnets, they should have high degree of retentivity, because even if there is a case of demagnetization, they should show the ability of this opposing demagnetization. Therefore, high retentivity, high coercivity. High retentivity, high coercivity, and high relative permeability. These are essential for a material to manufacture permanent magnets. Now let us take the case of what should be the materials better for electromagnets. Electromagnets, which we call them as popularly the solenoids, the coils and all. So which of the materials will be best for them? In such case, there actually this magnetization demagnetization cycle will be happening there because of that AC currents, and therefore low coercivity and low retentivity is an important character for making that electromagnet. Similarly, what about the material choices in the case of transformer? Because there also primary coil, what happens, AC current. We should discuss the transformer in detail in our next alternating current topics. But again, you will make a choice. Because there again magnetization demagnetization cycle is taking place because of the positive half cycle and negative half cycle of AC. In such cases, what type of core material we have to use so that the loss of energy is minimum. So like that, in the choice of the materials along with the mu r values, the important parameters are like retentivity and coercivity. So this is a complete discussion of hysteresis and hysteresis laws. Go through each and every point of the curve. You will get number of solutions. Yes. One more new topic, new unit. Let us go into the synapses. Please do remember, if you follow this class, name is synapses class, and you may expect that I am not doing examples. We will do 1 or 2 sessions examples as well for this. But do remember, follow the synapses, you will find a range of conceptual questions. In fact, this chapter, which we are now starting with AC circuits, happens to be a very, very easy topic. In fact, truly speaking, it is a very easy topic. Easy scoring topic as well. Of course, but not for all. Because why this becomes tougher? Because every time in a particular topic, I have told you, if it is electromagnetism or electrostatics or this electromatic induction, all these cases where the difficulty is with respect to drawing the vectors and using, of course, the conventions are also there in electromagnetics. And other cases, always writing the vectors, and that is why those topics become very difficult for many of the students. No question of these vectors and all, but why this becomes a bit difficult topic is, this is a collection. In this unit, we will see a collection of large number of topics. Small tidbits will find, but large in number. So because of this character, small tidbits and a range of parameters that we use, and it makes people difficult because they are not into the details of that. Second thing is that, one more thing, again, the terminology is such an important thing in science as a whole. In specific physics and in specific this particular topic I am telling you, the terminology that we are using is also very, very, very important. Because of these things, the students are feeling it very difficult. Rather, you will find those tidbits one after the other now we are discussing with. As a last topic of electromagnetic induction, we have told the case of a coil rotated in a magnetic field with specific axis, hope you remember, is giving rise to a kind of voltage signal which was a periodic, and that is what is called as alternating signal, whether it is voltage signal or current signal with the sine function and cos function, right? Now let us see what is that AC currents and voltages. Now this E is equal to E naught sine omega t, the voltage signal, or else I equal to I naught sine omega t. This is what is the AC equation. Now the point is that need not be sine always, because we know that both sine and cos both are periodic functions. Therefore, it can be here sine function or as well as cos function. Any of them is okay. Now, what I have told you about terminology. And here, these equations, you see this graph. In fact, this is nothing but a time graph. Time versus the magnitudes of voltages, the magnitudes of currents. Now here, this is a graph that I am using for our explanation part. Do remember, not always passing through origin, not always sine curve, not always cos curve. There are variety of the things, and that is what is the meaning that we have to take out of the graph. Now here, see here, starting from 0 and the y-axis, it is either voltage axis or current axis that I have taken, right? So here, this is what is the sine curve that we got, which means that it is 0 to maximum. 0 to maximum and again maximum to 0, right? This is what is positive half cycle. Similarly, we have again increasing and decreasing, but here what you find is the axis is reversed, and it means that the direction of induced EMF or direction of induced current is getting reversed, not changed. It is said, yes, the direction is reversed. So what you find from this is 0 to t, complete positive half cycle and negative half cycle. This is one cycle we call. So during one cycle, what all happening you can observe, because these are important things for all your conceptual questions, NEET and CET. What here you find is that, see, for every 0 to t by 2, the direction has a reversal. Again, t by 2 to t you will get, again sign reversal will take place. So the direction of EMF is getting reversed for every t by 2. Is that okay? For every t by 2, the direction is getting reversed. And similarly, what you find is that maximum to, 0 to maximum or maximum to 0. Though that variation, what is the time taken? This graph will tell you that as well. If this is what is t by 2 half cycle and this becomes t by 4, right? Symmetry is there, you will find. So 0 to t by 4 or t by 4 to 0. So for every time interval of t by 4, 0 to t by 4 or t by 4 to 0, in all such cases what happens? The variation is from maximum to 0 or 0 to maximum. So those changes are taking place. Reversal of directions, maximum, minimum changes. You will find many things, many such things from this graph. Okay, now here, this E0 refers to the peak value. See, this is what is the peak value, the amplitude we call for a wave, because we have represented a sine wave, right? So this amplitude part represents the peak value of either EMF or currents. And this LHSE refers to the instantaneous current which is changing with respect to time in a periodic way. So it is instantaneous value, the peak value, and this omega refers to 2 pi at the angular frequency. We know very popular in oscillations, and F is what is the frequency of AC. Frequency of AC. Now you see that we can have these kind of AC wave generators, and AC wave generators are popularly called as oscillators, which are based on LC oscillations. Remember there we have said omega is equal to 1 by root LC in the case of LC oscillation. That is what is made the principle for oscillator. So AC wave generators are called oscillators, and the circuit symbol I am writing here, the circuit symbol for AC generator, which is the oscillator, is yes, in a circle we will show one wave. This is one wave represented in a circle, and this is what is the AC source. We refer to the oscillator. Now generally when we are speaking about our household supplies, which we call line voltages, in the line voltage, do remember all the power generation will be based on the principle of coil rotation in the magnetic field, and therefore the supply that is generated is completely AC circuit, AC currents and AC voltages only, right? And this line voltage, when we refer to this F, or this F refers to the frequency of AC. In the case of line voltage, I am telling you, this frequency is 50 Hz, 50 Hz in India. Because again, that is about a technology that F value need not be 50 Hz everywhere in the world. In India, the AC frequency is 50 Hz. So the key word is line voltage, household supply, frequency, India, we can take it as 50. Otherwise, we will see for the data that is given in the question. Now, symbol. Now the point is that let us start by using our terminology now, right? Since it is constantly changing, change is constant here, you see. Since it is constantly changing, so what is that value that we have to refer to? Because the changes are there, generally we take it average values. But sometimes the average value may turn out to be 0, as in this case we will find the average values, there is a possibility of turning out to be 0. There we have the habit of introducing the values of root mean square values as well, right? Therefore here we are now going to introduce the average values and the RMS values for both for current and as well as EMF. I will be writing expressions for EMF or AC voltages, I'm sorry. For AC voltage, I will be writing the results, and the same we can use it for AC current. Instead of E, you will use I. That's the only difference. Now the first value is what is the average value. And as I have told you, please go through each and every statement of the teacher. You will find good number of conceptual questions and as well as solutions for it. For examples, average value, it is defined over 0 to T by 2. That is, it is defined over a half cycle. See, average value is defined over, can be a question, right? It is defined only over half cycle, because when we consider the total cycle, what happened? This average value and this average value will be equal and opposite, therefore average value over a complete cycle becomes 0. and that is why average value, it is defined only from 0 to t by 2. Even the definition as itself is the important question for you. We are now defining E average value is integral E dt 0 to t by 2 capital T the time period upon integral dt 0 to t by 2. This is the definition, and if we evaluate this integral by substituting a value of E and a simple integral calculus, the value that we get is yes, 2 by pi times E naught. 2 by pi times E naught, and it is nearly 63% of E naught value. So in the peak value, the 63% of that value of peak is what is referred to as average value. See, I am telling you 2 by pi times E naught, that is 0.63 times E naught. 63% of E naught is what is the average value. Now, other than average value, we also make use of RMS value, because average value turns out to be 0 during complete cycle. Therefore, now we are defining RMS value over the complete cycle. Therefore, remember, if I remove this average and write it as RMS value, which is otherwise also called as virtual value, please do remember, because in the given data, whenever you see virtual voltage, virtual current, they refer to, yes, root mean square values, and it is defined over a complete cycle, 0 to t. Over a complete cycle, we now define, and the definition is also an important thing for our CET or common-like examinations. It is integral 0 to t e dt by integral dt 0 to capital T, and this value happens to be 1 by root 2 times E naught. The integral evaluation will give you 1 by root 2 times, and it is nearly 0.71 times E naught. That is what is, and that is 71% of peak value is what is referred as RMS values. And now in general, unless and otherwise it is stated in the example, we always consider peak values and RMS values in our examples. Average values are very rarely used in the examples, but do remember that definition and the value as well. Now the point is that when we are using meters like ammeters and voltmeters to measure AC meters always measure RMS values, you should remember. They don't measure instantaneous values or peak values or average values. So AC meters, the readings that are given in the data, not to be taken as E naught or I naught, rather we should take it as, yes, E RMS or I RMS is one such important case. And now, after these two definitions, now one more important point we would like to give. Remember, in our discussion, you follow these tidbits in a sequence, and afterwards you just do about half an hour time. Again, I am telling you, very easy scoring topic for you. Now, we are telling one more definition, AC power. Power in AC circuits, when we are talking about, what is that? So this AC power will now give the expression only, we don't get into details, not required for us, right? AC power, we define it as power P is equal to E naught, the peak, I naught, the peak current, E naught, I naught times, yes, most important thing is cos phi. This is one important definition to remember. P, the average power we are calculating for AC circuits, E naught, I naught cos phi. This is our complete cycle, remember. E naught, I naught cos phi. Now we always know that what is, E RMS, I RMS, because we are taking complete cycle, right? E RMS, I RMS cos phi. Now E RMS we know, E naught by root 2, I RMS, I naught by root 2. If it is 1 by 2, root 2, right? 1 by 2, E naught, I naught cos phi. 1, 2, 3, 4 terms, any 3 terms given asked with the 4th term. That is how you will follow the lesson I am telling you. All these tidbits one after the other, and sometimes a combination of 2 tidbits or 3 tidbits. 1 by 2. And now let us come to what is this cos phi? This cos phi is called power factor of AC circuit. Power factor. I told you the terminology, very key thing. Cos phi, the power factor. And therefore you can see that this power factor now depends upon the phi value, and this phi is what is the phase difference. The phase difference, yes, between AC voltage and AC currents. Why this phase difference? What is the phase difference is our discussion in the coming topic. But remember, this P value depends not only on E and I values as in the case of steady current we discussed earlier, it also depends upon this power factor, that is the phase difference between them. Now to understand this phase difference and also some more details regarding our AC circuits, let us take up our next topic. Yeah, see, this is what is an important stage for our AC circuits. Further, all other topics depends upon these two important parameters that we now define. Always we know that whenever it is current, EMF we thought about, there is one property, natural tendency of the conductors by the name resistance, right? Opposing property for the free flow of charge carriers, SI unit ohm, and the reciprocal of resistance is what is called as conductance with the unit mho, ohm inverse, otherwise called as Siemens. Now, in specific for AC circuits, in earlier discussions of electromagnetic induction, the self-induction we did earlier, we did the case of capacitors. There we know that the natural tendency of inductor is to oppose the growth and decay of current because of the property of back EMF. See here, earlier we have told that graph, current or voltage graph, what happens? Current gradually increasing, decreasing, reversing direction, everything is taking place. Therefore, inductor, as its natural property, opposes the growth of or decay of current. This will cause an additional resistance for the AC. Apart from resistance, right? Now when we are using inductors in a circuit, AC circuits, even we can use it for DC circuit, what happens will be a discussion of words. But when an inductor used in AC circuits, what happens? It shows an additional resistance for AC. And similarly, capacitor has a property of tendency opposing the changes of potentials, the voltages. So again, AC voltages, variations and direction being reversed and everything. So capacitor opposes the growth and decay of voltages, and therefore it offers some special resistance for AC. That is what is referred as reactance in AC circuits. So these are reactance is the additional resistance offered by inductor or capacitor for AC, right? The symbol is capital X, and since we said it is by either inductor or capacitor, we have inductive reactance XL and capacitive reactance XC is what is our definition. XL reactance due to inductor, and this is what is reactance due to capacitor. Now earlier the reciprocal of resistance is taken as conductance with the unit of mho, ohm inverse Siemens. Similarly, what is the reciprocal of reactance? Can be a very simple CET common or NEET examination. The reciprocal 1 by X. The reciprocal 1 by X is what is called as susceptance. SUCCE, right? Susceptance. So again, reactance has the unit of resistance, that is ohm, and susceptance has the unit of mho, the Siemens, we can say. Now, this XL, inductive reactance, is given by omega times capital L. Omega, the angular frequency, the 2 pi F, frequency term is there, and L refers to the coefficient of self-inductance of an inductor, which was our discussion earlier in electromagnetic induction. Remember, XL is equal to omega times L. XL is equal to, I'm writing 2 pi FL. Therefore, XL proportional to F, XL proportional to L. Again, it can be either graphs or comparisons or the changes, percentage, etc. everything. So now, XL is equal to 2 pi FL. Now you remember, This is we said a special resistance for AC by inductor. If we consider DC, DC means no question of any frequency because no periodic changes. F is 0 and then XL equal to 0. So inductor, ideally speaking, inductor does not offer any resistance for DC. XL equal to 0 for DC. For AC also greater the frequency greater will be XL. Please do those, plot those graphs and any other things. Similarly, XC when we write the capacitive reactance, it is 1 upon omega C. 1 upon omega C. That is what is 1 by 2 pi F times C for the capacity of the capacitor. Here also will find the capacitive reactance depending upon the frequency, but this time it is inversely proportional. Therefore, if you draw a graph, it will be rectangular, hyperbola, negative slopes, very popular cases that we have discussed most of the times in classrooms. Similarly, this XC depending upon the value of capacity, also again inverse relation that you find, right? And again we said for DC, XL value happens to be 0 because F is 0, whereas for F0 in the case of DC, the steady currents, XC is infinity, right? Reactance, capacitive reactance is infinite for DC, and that is why do remember the capacitor once fully charged acts as an open circuit for DC. Why? What is the reason? Yes, this is what is the reason. XC is equal to infinity for DC, and this is for XL is equal to 0 for DC we have taken. Now, apart from resistance, AC circuits we got reactance X as well. Of course, XL and X again too. Now, in AC circuit, what will be the net resistance, the effective resistance, that is what is required, and that is given by a term called as impedance. You remember the terminology and you remember the expressions I am telling you. It is a scoring is such a damn easy. Impedance, and again the symbol we are using is Z, capital Z. Impedance Z. Again, impedance is analogous to resistance, which is the effective resistance we are calling. So the same unit, ohm. Dimensions the same of resistance, right? And the reciprocal of impedance. Every time resistance, reciprocal is conductance. Reactance, the reciprocal is we have told susceptance. Impedance, the reciprocal is called admittance. Yes, the reciprocal of impedance 1 by Z is called admittance. Now, impedance is given by under root R square plus X square is the question. R square plus X square. R is the total resistance in the circuit and the capital X is the effective reactance. Do remember, let us make one statement here. XL, XC, they now show a different tendency. What is it? Inductor opposes growth and decay of current, not for voltages. But whereas capacitor, it opposes growth and decay of voltages, but not currents. Therefore, because of this difference, the XL and XC, the tendencies are exactly opposite nature. That is, inductor does not, inductor shows the ability to show the opposition to the growth and decay of current, but not voltage. So voltage growth takes place, but not current at the same rate or in the same rate as that of voltage, right? And that is why, for that reason, any circuit with inductor, at the site of inductor, what happens? The current will lag voltage, or voltage will lead current at inductor. Is that okay? What is our statement? Due to this behavior of XL, current lags behind voltage. So the consequence of XL, let us write it as a statement here. Consequence of XL is, yes, current lags voltage. Current lags voltage, or else the other way also. Voltage leads current is also the case. Whereas when we are writing for XC, what is the characteristic of XC? XC always causes, yes, it is now opposing the variations or the changes of voltages but not current. XC will cause, yes, current to lead voltage. Current leads voltage. And that is what is referred as the phase. Earlier we have told about the power factor cos phi, where phi is the phase difference, either lagging or leading case. XC and XL will decide that phase difference in any AC circuits. Therefore now, when we are now writing impedance in a circuit, Z is equal to under root R square plus X square. Here, in fact, still clear way when we make it as a statement, this is R square plus. Supposing we have a circuit with only inductor, then it arises only XL, or only capacitors, then only the case of XC. Supposing we have a case AC circuit with both inductor and as well as capacitor, then XL and XC, because of their opposite natures, we have to take the net reactance as, and now here writing as XL difference XC. This X, the net reactance, will be taken as the difference of the two reactances, higher value minus lower value. XL difference XC whole square is what is the impedance of the circuit. So for AC circuits, in any given data, what about the resistance, what about the reactance, and what about the impedance? Because these things are going to decide many other parameters, which will be our discussion for tomorrow's session, along with a few examples. Have a great day.